During this segment, we will solve systems of linear equations by the addition method. So let's see what we mean by that method. Notice I have a system of linear equations, and I'd like to solve this system of linear equations. Now, thus far we've solved by graphing, but we found that that's not a very accurate method. We have one accurate or algebraic method called the substitution method. We are now looking at another method called the addition method or elimination method. But once again, here's my system. Notice that for this particular system, if I simply add these two equations, because I have x and negative x, the x's will subtract out. And that's okay to do in algebra. If we have this equal to this, the left side equal to the right side, and then this left side equal to this right side, it's true that this sum should equal the sum. The sum of the left sides will equal the sum of the right sides. So let's do that. Let's add the left sides, x minus x, that's 0x or 0, and then negative 2y plus 5y, that's 3y, is equal to, what is 8 minus 17? That is negative 9. And now notice what happens. Because the x's were eliminated by adding, we now have an equation in one variable y, and we can solve that equation for y. We'll simply divide both sides of the equation by the coefficient of y, which is 3. The left side then we have y. The right side, negative 9 divided by positive 3 is negative 3. So what does that mean so far? It means that this system has a single solution, and the y value of that solution is negative 3. How do we then find the corresponding x value of the solution? By using your knowledge of what it means to be a solution of a system. Remember, a solution of a system satisfies this equation and this equation. So we merely need to do the following now to find the corresponding x value. We just pick an equation in the system containing two variables, both x and y, and we let y be negative 3 and solve for x. It makes no difference which equation you pick in the system. I'll pick this equation, and I'll have x minus 2 times y is negative 3 is equal to 8, and now let's solve for x. So I have x minus, or you can think of this as negative 2 times negative 3, so that's plus 6 equals 8. Then subtract 6 from both sides, and if you do so, you'll have x is 8 minus 6, or 2. And that's our x value. Now I'll let you check. How do you check to make sure that this is the solution of the system? Let x be 2 and y be negative 3 here. Make sure it's a true statement. Let x be 2, y be negative 3 in the second equation. Make sure you have a true statement. You will, and then you are assured that this is the solution of the system. Now, of course, this doesn't always happen so that the coefficients of the x's or the y's are opposites of each other. But we can force that to happen. Let's look at this system of linear equations in two variables. I'd like to rewrite these equations so that we have equivalent equations, but either the coefficients of the x's or the coefficients of the y's are opposites of each other. Notice I have negative 2 for this coefficient of y and 4 for that coefficient of y. If I multiply the first equation through by 2, I'll have this coefficient being negative 4, and then of course this coefficient is still 4. The coefficients of the y's will be opposites of each other, and that's what we'll do. Let's take this first equation. We'll multiply the left side by 2, and the right side by 2. Now, how am I allowed to do this? Remember, by that multiplication property of equality, we can multiply both sides of an equation by any non-zero number. So I can do that, and I'll still have an equivalent equation. Watch what happens then. 2 times 3x, that's 6x, minus 4y is equal to 14. Make sure you write it down so you do not forget that you must multiply both sides of the equation by that number that you decide upon, and in this case it is 2. Now remember, this is equivalent to our first equation. We'll now simply rewrite the second equation. And now here's that system again, and notice the y's are opposites of each other. Let's now add the equations in the system. 6x plus 5x, that's 11x. The y's subtract out, and I have equals 14 plus 8, that's 22. Now I have an equation in a single variable x. Let's solve this equation for x. Here's my left side, here's my right side. Divide both sides by the coefficient of x, which is 11, and I'll have that x is 2. This is the x value then of the ordered pair solution of that system. Now, how do I find the corresponding y value? Well, you can let x be 2 here, 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 or here. Well, of course, that's the same as that. Choose any equation in 2 variables in this system. I'll just choose the second equation. All right, I'm letting x be 2. So I have 5 times 2 plus 4y equals 8. And now let's solve for y. 5 times 2 is 10. Plus 4y equals 8. So 4y is 8 minus 10, and that is negative 2. Then finish solving by dividing the left side and the right side by the coefficient of y, which is 4. And I'll have y as negative 2 over 4, but go ahead and simplify as usual. That will be negative 1 over 2. So the corresponding y value is negative 1/2. And this is the solution to the system. I'll let you check. Let x be 2, y be negative 1/2 here. Let x be 2, y be negative 1/2 there. Each time a true statement should result. This is the one solution of the system. Now let's look at some steps we can use then for solving systems of equations by the addition method. Step 1, rewrite each equation in standard form, that is ax plus by is equal to c. Step 2, if necessary, multiply one or both equations by a non-zero number so that the coefficients of a chosen variable in the system are opposites. Step 3, add the equation. Step 4, find the value of one variable by solving the resulting equation from step 3. Step 5, find the value of the second variable by substituting the value found in step 4 into either of the original equations. Then, of course, step 6, check the proposed solution in the original system. Let's go over those steps as we solve another system of equations. Now notice, each of these equations is written in the standard form ax plus by is equal to c. The fractions may be bothering you, and if that's the case, let's take what I'll call an intermediate step, and let's just remove fractions from each of the equations, and then we can move on and solve. In other words, just concentrate on the first equation for a moment. What may I multiply both sides of the equation by, and we'll no longer have fractions? The LCD is 3, so I'm just going to take this first equation and multiply the left side by 3 There's the left side. Do not forget you must also multiply the right side by 3. Now, at the same time, if you don't mind, let's look at the second equation because it contains fractions also. What could I multiply both sides of that equation by, and we will no longer have fractions? The LCD is 2, so in the second equation, I'll multiply the left side by 2. I'm rewriting that left side. And then do not forget you must multiply the right side by 2 also. So I will have equivalent equations in the system, just no longer having fractions. So let's go ahead and use the distributive property and multiply. Here, 3 times x over 3, the 3's divide out, and I just have 1x or simply x. I'm working on this first equation, minus 3 times y is 3y is equal to 3 times 2 or 6. And that certainly looks much nicer as a first equation in the system. Now let's look at the second equation using the distributive property again. 2 times this first term, the 2's divide out, and I'll have negative x over 1 or simply negative x. And then plus 2 times this term, the 2's divide out again, and I have 3y is equal to 2 times negative 3 or negative 6. So this is an equivalent system, looks much nicer, and notice it just happens that the x's will subtract out. If you need to at this point, you can certainly multiply one or both equations by other numbers. Just make sure whatever you decide on the left side of an equation, you multiply also that same number on the right side. All right, so let's go ahead and add these equations as they are. X minus x, that's 0x or 0. Well, it just so happens that this is 0, so I have 0 on the left side equals, and again I get 0. What does it mean when variable terms subtract out and I end up with a true statement, any true statement, 5 equals 5, negative 2 equals negative 2, 0 equals 0? It means that these equations are actually dependent equations. The graphs are the same line, and this system has an infinite number of solutions. So, infinite number of solutions. Why? Because all variable terms subtracted out and we ended up with a true statement. Now, if all variable terms subtract out and we end up with any false statement, 0 equals 5 or negative 1 equals 4, anything false, that means that we have then an inconsistent system, and it means that actually if graphed, the lines are parallel lines and the system has no solution. So keep that in mind when solving. Let's now solve this system of equations. This one just happens to have decimals in it, which is fine. Notice the first equation is written in standard form, second equation is written in standard form. This is now up to you. If you'd like, you can take a step and multiply each equation by an appropriate power of 10 so that you are no longer working with decimals. It's up to you. If we do that, I just need to, in the first equation, move this decimal point one place to the right. Same thing here, so I'll multiply the left side by 10. Do not forget you must multiply the right side by 10 also in order to have an equivalent equation. Now what will we do with the second equation? Well, 10 will work also. Don't think you have to use the same number. You have to use the same number on the left and the right of the same equation, but you don't have to use the same number for both equations, certainly, but left and right of that equation. So let's start multiplying. 10 times 3 and 5/10, that's 35, and then I have x, plus, move the decimal place one place to the right, and I have 25y equals 170. And then here, this is negative, so negative 15x minus 75y is equal to negative 330. There we have an equivalent system. Now let's look at the x's and the y's, and let's choose one of those variables. It makes no difference, but notice if I multiply the first equation by 3, I'll have 75y, and then I have negative 75y. So that's what I'll do. I'll multiply the left side of this equation by 3 and the right side by 3. Using the distributive property, 3 times 35, that's 105x, plus 3 times 25, that's 75y, equals, let's see, 3 times 0 is 0, 3 times 7 is 21, so there's my 1, carry my 2, and that's 510. Then I'll just simply rewrite my second equation. There we go. And now let's add those two equations because I know the coefficients of y's are opposites of each other. What is 105x minus 15x? Well, that's 90x. This subtracts out, equals, let's see, I have 0. I'll borrow. 11 minus 3 is 8. 4 minus 3 is 1. So I have my equation in one variable. How do I solve? I'll divide the left side and the right side by the coefficient of x, which is 90. The left side is x, and the right side is 2. So it looks like the x value of our one point of intersection is 2. So it looks like this system has one solution. The x value of that solution is 2. Let's now find the y value of that solution. Now, how do you do so? You can use the equations originally in the system. If you'd like, you can use the equations, the equivalent ones that did not have the decimal numbers in them. It's up to you. If you want to use that, let me just write one of them down. I'll write the first one down. Remember, we had 35x plus 25y equals 170. That's equivalent to the first equation. Now I'll let x be 2. So I have 35 times 2 plus 25y equals 170. 35 times 2 is 70. Plus 25y is 170. Let's see, 25y is equal to 170 minus 70, which is 100. And then I'll divide both sides by the coefficient of y, which is 25. And I'll have that y is 4. So the y value of the one point of intersection is 4. Now I'll let you check, and you really do need to check in the original equations. Now remember, here we have the original equations of the system. You really need to let x be 2 and y be 4 in each of these original equations and see that a true statement results. It will result. Here is your one solution. At this time, practice solving systems of equations by the addition method. To solve the system, 5x plus 3y is equal to 4, and 3x minus 2y is equal to negative 9 by addition, what step leads to elimination of the y terms when adding the equations? Is it choice A, multiplying the first equation by 2 and the second equation by 3? Is it multiplying the first equation by negative 3 and the second equation by 5? Or is it choice C, multiplying the first equation by 3 and the second equation by 2? This video will stop, then take a moment, see what it needs to happen for the y terms to be eliminated, and make your choice. Choice A is the correct choice. Look at this system. To eliminate the y terms, if I multiply the first equation by 2 and the second equation by 3, first equation has 6y, second equation has negative 6y. So choice A is the correct choice. Choice B is incorrect. Let's see why. I believe choice B eliminates the x terms. If we multiply the first equation by negative 3, this becomes negative 15, and the second equation by 5, this becomes 15. So you have negative 15x and 15x. So this step actually eliminates the x terms, and I was asking you to eliminate the y terms. To eliminate the y terms, notice you multiply the first equation by 2, this becomes 6y, and the second equation by 3, this becomes negative 6y, and that is choice A. So choice A is the correct choice. Choice C is not correct. Let's see why. If we multiply the first equation by 3, this becomes 9y, and the second equation by 2, this is 9y, and this is negative 4y, so the y terms will not subtract out. So choice C is not the correct choice. I believe you just have the numbers mixed up. Actually, if we multiply the first equation by 2, so that we have 6y, and the second equation by 3, so that we have negative 6y, then the y terms will subtract out. The correct choice is choice A.